The last few days we've been spending some time looking at convex and concave lenses. Yesterday, specifically, we took a look at the lens equation. 1 over f is equal to 1 over do plus 1 over di. And today, we want to do a lab that verifies that thin lens equation for one particular convex or converging lens. The problem, phrased in the form of a question, is the thin lens equation valid for a particular converging or convex lens? There are 3 variables, as always. 1 manipulated variable, and that should become pretty evident to you in just a few minutes. 1 responding variable, which also should become pretty clear in a few minutes here. And then, of course, you have a bunch of control variables, but there's always going to be 1 or 2 control variables that are really important, and those are the ones that I expect you to list. So we'll say 1 or 2 of those. The materials, you don't need to write this down. The materials, that's not part of your lab write-up, but just for your information, we're using 2 things. An optics bench apparatus, which consists of a meter stick. It consists of something to hold the meter stick. There's 2 little meter stick holders. One's in the picture, and then one would be over here out of the picture. You can see them right here. And one goes at either end of the meter stick, right? Just to hold the meter stick up so you don't have to hold it up with your hands. We've also got a candle and a candle holder right there. And during this lab, you're going to leave that candle at that spot on the lab at the 1 or 2 centimeter mark on the meter stick. And I'll explain why that is a little bit later on. You're also going to have a screen and a screen holder and a lens holder. Now, I've listed the lens separately just because technically it doesn't come with the apparatus. So it's 2 things that we have. Now, how is this lab going to work? Well, the first thing you're going to do is find the focal length of your lens. We talked about that the other day, right, when we aimed it at the Canada flag and saw where the rays from that flag intersected or converged. They converged essentially at the focal point. What you want to do today is aim your lens at a far-off object, further away than I did the other day in the demonstration. Like maybe the condo's across the street, or maybe you go down to the end of the hallway here, flip off the lights and aim it at the house across the street by the golf course. Aim at something far away. Those rays of light coming off of that object that make it through that thin, narrow lens are going to be effectively parallel to each other, which means where they converge will be the focal point. When you see an image of that house or that condo or that car moving up the street, okay, that's going to be the distance, or the distance between the lens and the card is going to be the distance that represents your focal length. Does that make sense? Today's a perfect day. It's bright sun outside. We want a brightly lit object to find an image of. The only thing is you got to be careful of is that you're doing this at a bright object from a darker area. So if you're standing in this room, you don't want to make that big blind wide open. Okay, just open a corner of the blind, turn off the lights, stand in the dark area away from the outside light, and aim it at that one thing. Why do we not want all this ambient light around where we are? We're not going to see the image. It's going to wash out the image, right? There's going to be too much other light that washes out what you're supposed to see. So stand in a dark area, aim it at a bright object, and move the card back and forth like we did the other day in the demonstration until you see a good, sharp, focused image of that object on the screen. Once you have your focal length and you've recorded the value of that focal length, now you want to do the main part of the experiment. The main part of the experiment involves placing your object, which for us will be a candle. A candle, why? Anybody? A candle generates light. Now, it's better to use something that generates its own light than something like a water bottle, let's say, that reflects its light, because in order for this to reflect light, we have to have the lights on. If we use a candle, we can keep the lights turned off, no ambient light or very little ambient light to wash out the image, just generate the light from the object itself. So we're going to use a candle as our object. We're going to place that, as I said a few minutes ago, down at the 1 or 2 centimeter mark. It doesn't really matter which, okay, but place it down at the end and leave it there. Then you want to place your lens and your lens holder a certain distance away from that object. If your focal length was, let's say, 10, your focal length, by the way, should be somewhere between 10 and 20, depending upon the lens. Let's say it was 10. I want to make my first object distance, and in fact, all of my object distances, greater than 10. If I make my object distance 10, and my focal length is 10, there will be no image. If I make it less than 10, the image will be virtual, and I'm not going to be able to see it on the screen. So I want my object distance to be greater than 10. Listen, if you have a focal length of 10, I'd start at probably about 15, as opposed to 11. Start a little bit above, right? Start at about 15. So keep your candle there. Put your lens, let's say 15 centimeters away. That would be my object distance. And then you're going to move this card back and forth until you see a good, sharp, focused image of the flame flickering about on that card. Then you're going to measure this distance from the lens to the card, and that will represent your image distance. Does that make sense? So if you're recording your focal length, which is going to stay the same throughout the whole experiment, then you're going to create an object distance that's greater than your focal length, and then you're going to measure how the image distance ends up, what the image distance ends up being in response to whatever the object distance was. Then what do you think you're going to do? Well, you're not done. Far from it. What do you think you're going to change here? What do you think you're going to manipulate? Not the focal point. Okay, you're going to keep that same lens the whole time, so it's going to have the same focal point the whole time. The object distance, yeah. I would increase your object distance to maybe 20 centimeters. Okay, make it 20. Make it a bigger object distance. Move the card back and forth in order to see where it needs to be in order to get a good, sharp, focused image of that flame on that card. Keep doing it. Do it like 10 times until you get 10 different, one focal point, 10 different object distances, and 10 corresponding image distances. All right? Now, I got a little picture for you to see, just to demonstrate what you're supposed to be looking for here, okay? One of these works, and one of these does not. If you take a look at the left diagram here, I'll flip off the light so you can see this a little bit better. If you look carefully at that, I know it's a little bit small from where you are, but you should see a focused image, and a smaller image of an inverted flame. You see that? That's focused. That's what we want to see. Over here, if you look at it, you see just a circle of light. That's light going through the lens. Light's always going to go through the lens, but that's not producing a focused image on the screen. So that's not what we want to see. Okay, you see this? Okay, that's not good enough. You got to move the card back and forth a little bit more until you see the candle, or the flame, I should say, flickering about. All right? So what's your data table going to look like? Something like this. Your focal length, I said for mine was 10 centimeters, but yours could be 12 or 15 or anything like that. Object distance times 10. Image distance times 10. What do we usually do when we have a table like this? Plot a graph, or create a new table. It's one of the two, right? It's either create a new table and then plot a graph, or it's plot a graph right away. This time we're going to create a new table, an analysis table. This is data, this is analysis, where we're going to take the inverse of all my object distances and the inverse of all my image distances. So if my first object distance was 10, 1 over DO will be 0.10. If my second object distance was 20, then my second 1 over DO will be 0.05, and so on. Literally just flip them over. You can do that on your calculator, or you can do that as a function in Google Sheets. Either one works just fine. Then you're going to plot a graph. This is the second column of my table, so it's going to go on my y-axis. This is the first column of my table, so it's going to go on my x-axis. 1 over DI versus 1 over DO. What do you think the shape of the graph is going to be? It's going to be a straight line. But a different straight line than you've seen before in any of the other labs that you've done. This one is going to look something like this. It's a straight line. We can do y equals mx plus b because it's a straight line. But what's different about this? I'm sorry? It's got a plus b. Yes, exactly. It's got a y-intercept. It clearly has a y-intercept here, right? If it's sloping downwards, it's also going to be a negative slope, right? That means with a negative slope, there has to be a y-intercept there. All right, so how do we deal with this? Straight line, what do? Y equals mx plus b. Let's start with that. Y is equal to mx plus b. That's the equation from the graph. Y gets replaced with? No. Y gets replaced with 1 over di. M gets replaced with, Colton, M gets replaced with slope, yes. X gets replaced with 1 over dO, yes. And we cannot cancel out or cross off B this time because there clearly is a y-intercept. So for the first time, we're doing one of these problems involving graphs where there is a y-intercept. Now let's identify an equation from my data sheet that has the same variables in it. 1 over dO and 1 over di. Which one is it? Yep. Good. It's the equation we learned yesterday, the lens equation, right? 1 over f is equal to 1 over dO plus 1 over di. Now, what do I want to solve for in this blue equation here? I don't want to solve for f yet, no? Sorry? Somebody said it? I want to solve for 1 over di. How come 1 over di is in? I want to make it look like the other one. So I'm going to say 1 over di is equal to negative 1 over dO plus b. I could have said, sorry, not plus b, but plus 1 over f, right? I could have said 1 over f minus 1 over di. Why did I put it in that order? Well, Isaiah alluded to it when he gave the reason why we solve for 1 over di. I want to make it look as much as possible like the other one. And the other one is something times 1 over dO plus b. I got something times 1 over dO plus something. Start crossing things off now. 1 over di disappears because it's in both. 1 over dO disappears because it's in both. What am I left with here? The slope is equal to what? Negative what? Nope. Negative 1. Who said that? Good. The slope is equal to negative 1. It's kind of weird. No matter what data you have, you will get a slope of negative 1. So will you, so will you, so will you get a slope of negative 1. Or at least, theoretically, you should get a slope of negative 1, right? It's independent of your data. The slope should be negative 1 independent of your data, as long as you have valid data, that is. What are we left with over here? B is equal to what? 1 over f. Google Sheets will give you the value of b, so you're going to solve for f. But wait a sec, we already have f, right? We measured it. So what do you think you're going to do to test to see if the thin lens equation is valid? Yeah, percent error. You're going to compare the two. So compare your calculated f with your measured f. And what's usually our threshold for saying that something is verified? About 10%, yeah. So we'll say that if the percent difference is less than 10%, the assumption that we made, which is this equation, must be valid. That was the whole problem, right? Is this equation valid? Well, we assumed it was valid, and since the numbers were within 10% of each other, our assumption is correct. And if it's greater than 10% error, then our assumption was incorrect, and that's fair enough. Conclusion comes next. Is the thin lens equation valid for a particular converging lens? Yes or no? How do you know? Well, just give a brief justification as to how you know that it either was or was not verified. And then, of course, your sources of error. And don't forget your suggestions for improvement on that source of error. The equation question here, the equation for percent error is, this doesn't go with conclusion, right? This goes with analysis, but the question was just asked here. The percent error is actual minus theoretical over theoretical. And we take the absolute value of that so that we always get a positive percent error, and then we times it by 100. Another way you could phrase that would be calculated minus measured over measured times 100. So that would be the one that you got from your graph minus the one that you initially got over the one that you initially got times 100. So what do you got to hand in for this? I do want you to hand in a problem, although you can see that's not italicized because I gave you the problem. Every lab needs to have a problem, right? You can't conclude something without a problem. This is what you're really going to get marked on here. Your variables, your data, your analysis, your conclusion, and your sources of error.